Laser-light has several unique properties that no other light source can match. The monochromaticity and excellent directionality of laser light are its most notable characteristics. The most of light sources are made up of waves with wide wavelength bandwidth. Laser light has an extremely narrow bandwidth. This is due to the fact that the light generating process is only related with two energy levels. Only photons of the same wavelength will be generated if energy levels are very sharp and represented as lines. The interaction between the raging atoms and their surroundings, however, has widened the energy levels a little. As a result of this broadening of energy levels, even laser light is made up of waves of different frequencies, result in waves with a narrow bandwidth. The FWHM, which means full width at the half maximum in the spectrum, is a measure of light sources monochromaticity. The full width of the wavelength at half the maximum intensities in the spectrum is referred to as the FWHM. The FWHMs of laser light and gas discharge light are compared in the figure. However, they are not drawn to scale. The center wavelength of and FWHM of light from cadmium lamp, for example, are 643.8 nanometer and 0.013 angstrom respectively. So the full width at half maximum means the full width of the wavelength at half maximum intensity. So FWHM represents this wavelength width. In comparison to other light sources, cadmium lamp has excellent monochromaticity because the FWHM is just 0.013 angstrom, so very narrow bandwidth. However, it cannot be compared to laser light. The FWHM of helium neon laser, on the other hand, is substantially smaller at 10 to the minus 7 angstrom compared to the FWHM for cadmium lamp is much smaller. The helium neon laser's central wavelength is also around 632.8 nanometer, which is similar to that of cadmium lamp. The monochromaticity of the laser light is uncomparably noted, as can be seen from numerical data. So we can compare these two FWHMs. So it's uncomparably noted data. Laser light is commonly utilized for optical communication using optical fiber systems due to its excellent monochromaticity. Helium neon laser light has FWHM that is approximately 10 to the 5 times smaller than the cadmium lamp light. This is because the laser's stimulated emission process only involves two energy levels for lasing. On the other hand, several atomic energy levels are involved in the light produced by spontaneous emission process in the cadmium lamp. The excellent directionality of laser light is the second distinctive feature. The stimulated emission is responsible for these characteristics of laser light. The light photons emitted by stimulated emission have the same frequency and phase as twin photons. As a result, laser light can transmit a considerable distance without spreading. This excellent directionality property can be used to focus all of the laser light's energy into a small region. That is, in the material process, laser light can be used for cutting, welding, and drilling. In medical applications, the laser is also utilized as a surgical light. Due to the excellent directionality of laser light, all of these applications are possible. Lasers are named after the laser media that they use. There have been various lasers developed, including solid, liquid, and gas lasers. We will go through some solid, liquid, and gas lasers in detail. First, let's see the ruby laser. Maiman developed the ruby laser, the first visible laser, in 1960. It is referred to as a solid laser. A solid laser's laser medium is usually a solid material with a few % of rare earth metal doped in it. The energy levels of rare earth atoms in solid materials are well defined. However, if a large number of rare earth atoms are doped into a solid material, the energy levels of rare earth atoms become complicated as a result of interaction between doped atoms. As a result, the amount of doped atom should be kept to a few % at most. Ruby is a material in which chromium atoms have been doped. In alumina Al2O3, chromium atoms have replaced aluminum. As the amount of doped chromium in the ruby increases, the color of the ruby changes from pink to red. In alumina, chromium atoms exist as chrome plus 3 ions and act as raising atoms. This figure depicts the energy level of chrome plus 3 ion. It contains absorption bands in blue and green, which are employed as pump levels in this laser. Pumping is done with optical energy since the absorption bands correspond to visible light. The ruby radius should be small so that optical energy can pass through the rod center. Ruby rods with a radio of about 2 mm are commonly used as a laser medium. This ruby laser is a 3-level laser. So this is a pumping level, and this is metastable state and ground state. So ruby laser is a 3-level laser. And the wavelength of laser light is red, whose wavelength is 694.3 nanometer. Depending on the amount of chromium in it, rubies range in color from pink to red. Blue and green absorption bands, these bands, are observed in chromium ion. The figure below depicts the ruby laser's schematic structure. The ruby rod is wrapped by spiral-shaped flash lamp. This is ruby rod, and this is a spiral-shaped flash tube. By observing the green and blue light from the flash lamp's prism light, the chrome +3 ions in the ruby rod are excited to pump levels. After being excited to pump levels, chrome +3 ions have now dropped to the metastable state. Between the metastable and ground levels, a population inverse is formed. The ruby laser has a wavelength of 694.3 nanometer, a red color. As could be seen in the energy level diagram, the ruby laser is 3-level laser. The resonator is constructed by polishing both ends of rod and coating silver to those surfaces. From one end of the rod, laser light is emitted this direction. Ruby rod used as the laser medium has a diameter of 2 millimeter and is enclosed in a flash tube with a spiral shape to provide the pump energy. Blue and green color absorption bands exist in the chromium ion energy levels in rubies. In order to form a resonator, the rod's ends are coated in silver. Now let's see a semiconductor laser. A p-n junction is the structure of a semiconductor laser. If the p-n junction is forward biased, electrons and holes from p-n, n and p-type semiconductors cross the depletion region and recombine. When electrons and holes recombine, light photons are emitted. The semiconductor laser has a structure that is identical to that of LED, light emitting diode. However, in order to achieve population inversion, the p and n-type semiconductors in the semiconductor laser are more heavily doped than in LED. The end faces of semiconductor lasers should be polished to form a resonant cavity. There is an energy gap between a band at the ground level, we call valence band, and a band at the exciter level, we call the conduction band. There's conduction band and valence band. The excited state as ground state. The energy can be released as a photon of light when an electron descends from the conduction band and fills hole in the valence band. Because electrons moving from conduction band to the valence band to fill the hole there. In a laser or LED, the energy of photons emitted is roughly equal to the energy gap, which is given by this equation. This energy gap, and that's energy of a photon. So mu is frequency of the photon, h is Planck constant. As a result, the wavelength of photons emitted is given by this equation. The energy gap of the semiconductor used as the active laser determines the wavelength of the light emitted by the laser or LED according to this relationship. So, energy gap then determines the wavelength of the emitted photon. Edge semiconductor cannot be used in a laser or LED's active layer. In some materials, the energy band of solid matter is generally complex and difficult to figure out. Direct band gap semiconductors are a type of material that can be used for laser or LED materials. Silicon is material with an indirect band gap, hence it cannot be used for laser or LED materials. This is a energy band diagram for direct band gap semiconductor, and this energy diagram for the indirect band gap semiconductor. So only direct band gap semiconductors can be used for laser or LED. Both energy and momentum should be conserved as the electron moves from conduction band to the valence band. In an indirect band gap material, electron moves from the bottom of the conduction band to the top of the valence band through a significant change in momentum as seen in the figure. So direct band gap semiconductor, electrons move to the valence band. There's no momentum change here, but in indirect semiconductor, electrons here, the bottom of the conduction band, and these electrons move to the top of the valence band. So in that case, there is a lot of momentum change here. Okay, but in this direct band gap semiconductor, there is no momentum change. In the semiconductor with a direct band gap light figure, the descending electrons to the valence band experience no momentum change. See here. However, in a semiconductor with an indirect band gap left figure, like silicon, satisfying momentum conservation causes the descending electrons to almost lose energy to the lattice. So electrons should conserve momentum conservation law, so its almost energy is lost to the lattice. As a result, an indirect band gap semiconductor cannot be used as a laser medium since electron-hole recombination rate is insignificant to emit light. Okay. To conserve both energy and momentum, the transition produces a quantized collection of lattice vibrations known as phonons. As a result, all of the energy of electrons descending from the conduction band into the valence band ends up heating up the crystal, resulting in lattice vibration phonons. As a result, if we use indirect band gap semiconductor materials, we cannot expect light to be emitted. This behavior indicates that the rate of recombination of electrons and holes in the indirect band gap semiconductor materials is extremely low, preventing sufficient radioactive transition. The transition from the conduction band to the valence band in a direct band gap semiconductor, on the other hand, requires almost no change in momentum. So, photons have a very small amount of momentum. As a result, they have a lot of energy to recombine with the valence band's holes. By simply emitting a photon of light, electron-hole recombination in the direct band gap semiconductor conserves both energy and momentum. When an electron and a hole recombine, this radiative transition causes light to be emitted. The recombination rate of electrons and holes in direct band gap semiconductor materials is high enough to emit photons of light according to this phenomena. The population inversion is formed by forward bias in the energy band diagram as seen in the figure below. This figure. So here forward bias is applied. Then we have here population inversion is formed. Light photons are produced when electron and holes recombine in the active area, this area. Light is emitted by the spontaneous emission process up to a threshold current, up to here, threshold current. However, once the threshold current is exceeded, the laser action begins and stimulated emission prevails over spontaneous emission in this region. The efficiency of the conversion of electrical energy into light rapidly increases beyond the threshold current. In 1962, the first semiconductor laser was developed by doping gallium arsenide to form a p-n junction. To maintain the population inversion, this so-called homojunction laser needs a lot of current. The heat produced by continuous high current quickly destroyed the device. As a result, at cryogenic temperatures, this laser operated in the pulse mode. A narrow strip electrode was employed to prevent current overheating. This is narrow strip electrode. Instead of flowing current over a large area of diode surface, we can use this narrow strip to flow current only along a narrow strip. this width of this much of width. As a result, maintaining the population inversion with a higher concentration of charge carriers in a stripe region allowed for steady laser operation without overheating the laser. Using heterojunction structure, we can improve the current confinement and the efficiency of laser operation. So later, heterojunction structure was used. So if you use this heterojunction structure, then current is confined. So the efficiency of laser action is improved. This shows the heterojunction laser. Heterostructure semiconductor laser. A layer of P gallium arsenide will act as the active region. This active region. This layer is sandwiched between two layers having a wide band gap, P gallium aluminum arsenide and N gallium aluminum S arsenide is 2. So this active layer is sandwiched by these two confining layers. The end faces of the junction of P gallium arsenide and N gallium aluminum arsenide layers are well polished and parallel to each other. They act as optical resonator. So this end and the other end here is polished, and we coated refracting coating with the refractive coating both on both sides. Then this forms the resonator. Okay. In contrast to homojunction diode, which has just one junction, the heterojunction diode has several junctions of the similar materials. So we can see here. The active layer is a narrow region where electrons and holes combine. The refractive index of the active layer is higher than that of the material above and below it. So the refractive index of this active layer is larger than that of these two confining layers. Then the emitted photons in the active layer are then refracted via total internal refraction of the interface between the materials and confined within the active layer's thickness. So the generated photons, so there are two confinement layer, and this is active layer, and photon is produced inside the active layer, and this photon refracted back to the active layer, total refraction. So photons are confined between these two confining layers. So the photons are completely confined between active layers thickness. So just inside here. Quantum mechanical effects become important when the active layer thickness is less than tenths of 4 nanometers, and the injected charge carriers from N and P-type semiconductors are entirely confined in the narrow region. So in this active layer region, okay. As a result, by concentrating light on the active region, which acts as light guide, so this acts as a light guide. So these two confined layers acts as a light guide. The efficiency of the stirring emission improves. Okay? Quantum waves are a type of ultra-thin structure. So we can also use the quantum wave structure for the confining layer. Charge carriers are confined to a restricted area by striped electrodes and quantum wave structures. This technique allows a semiconductor laser to operate continuously at room temperature. In contrast to a typical diode laser, light can be produced to emerge from laser's surface rather than the edge. This type of laser is known as a vertical cavity surface emitting laser, so VCSER. So light is emitting from the surface of the laser. We saw the edge laser, light is coming from the edge, but and this VCSEL laser, laser light is coming from the surface of the laser. Okay. The VCSEL's structure is depicted in figure below. This figure. In conventional diode lasers, the cavity is horizontal. In a VCSEL, on the other hand, cavity is in the vertical direction. So here, cavity is this and that, forms the resonator. So resonant cavity is formed by multilayer mirrors above and below the active layer. So these two forms the resonator. As a result, VCSEL is a surface laser, whereas conventional lasers are edge lasers. The VCSEL solves the problem of diverging and elliptical beam produced by an edge emitter's small and irregular emitting surface. If we use the VCSEL as a light source and optical communication device, it has many advantages. The optical communication chip may be examined before the optical communication device is constructed, since the laser light emits from its surface. However, if we utilize an edge light emitting laser, we can test the optical communication device after it has been put together. So after assembled, then we can test the optical communication device. But if we use VCSEL, then we can test the optical communication device before assembling the communication device. the devices, the production costs are significantly reduced as a result, because we can test the optical communication device before assembled, so we can reduce the production cost. Since the VCSEL generates light vertically, thousands of lasers can be manufactured simultaneously on a 3-inch gallium arsenide structure. So light is coming from the surface, so we can construct this VCSEL lasers on the 3-inch gallium arsenide surfaces. Table below summarizes common semiconductor laser materials and their laser output wavelength. The bandgap energy of compound materials can be modified by changing the relative amounts of constituent elements. So we can change the relative amount of this gallium or arsenide amounts. Then we can, not for this one but here, we can change the relative amount of the constituent elements. Then we can change the output of the laser. For this case, the output range can be changed from 750 to 850 nanometer by changing the relative amount of this constituent elements. The bandgap energy of the lasing material determines the wavelength of the laser output. As a result, different composition ratios of constituent materials can be used to produce different wavelengths of the laser output. As can be seen in this case, we can also obtain some different wavelength of laser by changing the amount of this constituent elements. This also we can change the output wavelengths. Okay. So we can alter the wavelength of the laser light by varying the relative amounts of the component elements in the semiconductor laser material. For example, nitride materials like aluminum nitride, gallium nitride, and indium nitride can be combined to create visible light lasers, such as aluminum gallium nitride and indium gallium nitride lasers. So this shows that the resulting alloy, commonly abbreviated as gallium nitride, for this case, we can call just simply a gallium nitride, can be potentially be mixed using formulas this and this to create any band gap that is located within the visible spectrum. So changing the amount of constituent elements, we can get different laser light, different wavelengths laser light. This is visible laser. Others this ultra red, and most of the semiconductor lasers are in the range of the ultra red frequency wavelength. But gallium nitride The output of this laser is the visible light. The others ultraviolet range. Now let's see the dye laser. Several liquid lasers have been developed to date, but dye laser is the most important. The dye laser has the advantage of being able to tune over a wide range of wavelengths. The laser medium of a dye laser is an organic dye dissolved in a solvent. When a dye is excited by a certain light source, it emits light with longer wavelengths than the light that was observed. So there's absorption light wavelength and this emission light wavelength. So emission wavelength is longer than that of absorption light. This is called fluorescence. The wavelength mismatch between the observed and the emitted light is caused by the heat generated by laser medium. The figure below depicts the fluorescence spectrum of typical dye. So absorption wavelengths and emission wavelengths are different. The figure depicts the energy level diagram of a common dye. This figure. When the total spin of the excited electrons in each molecule is zero, the singlet states occur. So we call S0, S1, S3. So total spin is zero in the singlet state. So this one, this diagram shows the singlet states. The triplet states T1 and T3 on the other hand happen when total spin is unity. Total spin is 1, then we can have the triplet states. The vibration and the rotation of dye molecules as well as the effects of solvent molecules broaden each energy level into numerous sublevels, forming a near continuum. So there are so many vibration and rotation modes, so we can have nearly continuum energy levels in a singlet and also in triplet states. We have various rotation and vibration energy levels here. The broad fluorescence spectrum is the result of this broad energy level. The figure depicts the laser action processes of a dye laser. Optical pumping is used to move dye molecules from the ground level S0 to the highest sublevel of the first excited level S1. So if we supply optical energy, then dye molecules and the ground state move to the excited state. Okay. The molecules then undergo a very rapid non-radiative decay process to reach the lowest sublevel of S1. So here in this process, radiation decay from this level to the bottom of this S1 level. When the molecules drop from the excited level to a level in S0, so here the molecules are moving to the ground state. So molecules can move for many choices for the energy levels in ground state. Okay. The laser light is emitted. Within S0 and S1, there are numerous rotational and vibrational energy levels. As a result, there are numerous possible transitions between these levels. So there are so many possibilities for molecules moving from this level to the ground states. So consequently, the dye laser spectrum is pretty broad. The dye laser is a 4-level laser as shown in the figure. So dye laser is a 4-level laser. Due to the numerous rotational and vibrational motion of the dye molecules, the energy levels of the dye split, yielding a broad range of laser output. Even though quantum mechanical selection rules forbid it, there is a small chance of transitioning from the singlet state S1 to the triplet state T1. Quantum mechanical selection rule forbid the transition from S1 to T1. There's a singlet state and there's a triplet state, so quantum mechanical selection rule does not permit the molecules moving from here to here. But there is a small chance of transition from these two states, because T1 to S0, this direction, is also forbidden, so it's not possible. The molecules pile in T1, so molecules cannot move to this ground state, so molecules pile up in this triplet state. The transition from T1 to T2 is, on the other hand, is allowed. Okay, so these molecules cannot move to this ground state of a singlet state, but molecules can move to the excited state of the triplet state. Furthermore, the difference in energy between T1 and T2 is the same as difference between S0 and T1. So this energy difference, no, this energy difference and this S0, or this difference, this energy difference and this energy difference are nearly the same. Okay. So absorption of pumping energy by the T1 to T2 transition. So if we apply pumping energy to the dye molecules, instead of make transition from molecules in this state to the excited state, this energy can be used to transition of these molecules to the triplet ground state to the triplet excited state. So energy is lost, pumping energy lost. Okay. So as a result, absorption of pumping energy by T1, T2 transition reduce gain and may cause the laser to stop working. In most cases, a significant transition of molecules to T1 takes roughly 1 microsecond. As a result, most dye lasers use short pulses of less than 1 microsecond. When oxygen molecules are mixed with dye liquid, the excited dye molecules in T1 are assisted in their drop to S0, so in this direction, by oxygen molecules. Furthermore, circulating dye liquid through the dye cell can drastically reduce the population in T1. So this circulation makes the dye avoid decomposing due to too much heat. So usually in dye laser, dye liquid is circulating, and also oxygen molecules are mixed with dye molecules. Despite selection rules restriction on the transition from singlet to triplet states, some of the molecules that were pumped to the singlet S1 moved to the triplet T1, so in this direction, which stopped the laser's operations. Dye liquid is circulated in order to solve this problem. The dye laser can also be operated in a continuous wave mode in this manner by circulating the dye molecules. The figure below shows a schematic diagram of a dye laser. Pumping is done with the help of other lasers. We can use other lasers for pumping using a prism or diffracting grating, this one. The laser output can be controlled. Two concave mirrors act as resonator. Oh no, it's not correct. Okay, let me say again. Using a prism or diffraction grating here, so tuning device, we can use a prism or a diffraction grating. Then we can select the wavelength of the laser output. The laser output of the dye laser is broad spectrum, so we can choose one wavelength by using a prism or diffraction grating. So using a prism or a diffraction grating, the laser output can be controlled. So here, the tuning device. Two concave mirrors, this and that, acts as a resonant cavity, focusing the pumping light onto the dye cell. So here, focusing the pumping light on the dye cell. We can acquire a wide wavelength range of laser output depending on the dye molecules used. The wavelength ranges of various dyes are as follows. polymetallic dye, the wavelength limit is 0.7 to 1 micrometer, and xanthine dye, that's visible light, coumarin dye has ultraviolet vision, and scintillator dye, that's ultraviolet. This polymetallic dye, we can get the output of ultraviolet vision. Now let's see the gas laser, the helium-neon laser. The helium-neon laser uses a gas mixture of helium and neon as its laser medium. Helium has a 5:1 ratio with neon, so we put much more helium. This gas mixture is vacuum sealed in a tube with a few millimeters in diameter. The tube's length varies from 0.1 meter to 1 meter. The gas in the tube has a pressure of around 10 torr. The figure depicts the laser action processes and energy level diagram. This figure. The electrons from the electrodes at the tube's ends excite helium atoms when a high electric voltage is given to them. So it's a tube is here. Inside this tube, helium and neon gases are filled up to the pressure of about 10 torr. And here electrode. So we apply high voltage between two electrodes. Okay. Then the electrons from electrode comes out due to this high voltage, and so the electrons from electrodes at tube's ends excite helium atoms here, helium atoms collide with the helium atoms when a high electric voltage is given to them. The excited helium atoms collide with neon atoms. So excited helium atoms collide with neon atoms, which causes them to be pumped to higher levels. So due to the high energy electrons, the helium atoms in ground state move to this pumping level, and these excited helium atoms collide with neon atoms. So the bump levels, which act as upper laser levels, are metastable. So this is metastable state. So raising material, raising gas is neon. Helium is used only to excite the neon atoms. Actually, the raising gas is neon. So this excited state of neon is metastable. The laser output is emitted when the excited neon atoms drop to lower energy levels. So this level. So there are various laser outputs. By colliding with the wall, neon atoms decay to the ground state and are ready to be pumped again. So this laser action is done in this transition from this metastable state to this lower laser level. We have various sub-levels, so we can obtain the wavelengths of various wavelengths output. But usually we use this 632.8 nanometer, the red light, for neon laser. So by colliding with the wall, neon atoms decay to the ground state and ready to be pumped again by colliding with excited helium atoms. Since the excited states of the helium atom are very close to the neon atom's pump level, the helium atoms are employed to pump the neon atoms to that level. The neon acts as a medium for aging. As a result, we can see that neon atoms cause the laser reaction, whereas helium atoms help to excite the neon atoms. Helium can perform this role because its excited energy levels are same to those of neon atoms. Several different neon atom transitions provide various laser output. We can choose the wavelength of the amplified laser output by adjusting the angle, burst angle of the tube ends. Or if we change this angle, we call this burst angle, then we can choose the laser output. We saw that there are several different wavelengths of output, so we can choose one of them by changing this angle, so angle of tube. However, most helium neon lasers operate at wavelengths of 632.8 nanometer, which is red color. The figure below shows a schematic diagram of helium neon laser. This one. Following the laser action, neon atoms collide with the discharge tube's wall, this wall, and decay to the ground state. As a result, the tube's diameter should be small to allow for the rapid decay of neon atoms to ground level. So, diameter of this tube should be small. By changing the angle of the tube ends here, the laser output can be selected. However, the output of 632.8 nanometer is preferred by the majority of helium neon lasers. The tube's diameter must be very small for the laser-active gas atoms to rapidly decay to the ground state by colliding with the tube walls and become available to continue laser action. This table shows various kinds of lasers, gas laser, liquid laser, and solid laser. We already saw the structures of helium neon laser, gas laser, one of the gas laser, and we have gas laser, CO2 laser, and N2 laser, argon ion, and argon fluoride, is called the extreme laser, and wavelength is visible, red, and the CO2 laser, the wavelength of output is infrared region. N2 laser, it has blue color. Argon ion laser is also blue color. Extreme laser, the wavelength of output is ultraviolet. This column shows the output power, and CW means continuous wave, and pulse laser. Okay. Liquid laser is dye laser, so wide range of wavelengths, so depending on dye. And CW laser, and we can tune the output wavelength by using the prism or grating system. For solid laser, we have ND-argon laser, ND-glass, semiconductor lasers, and others. There are various kinds of solid laser. ND-argon laser, its output is infrared, and glass is also infrared. And semiconductor, depending on the semiconductor material, we can have various wavelengths output.